Good morning student, welcome to all. Last class we discussed what is P-type semiconductor and what is N-type semiconductor. Actually there is two types semiconductor, intrinsic and second one extrinsic. Intrinsic semiconductor means it is pure form and number of hole and number of electrons are same. But in case of extrinsic semiconductor, we have to add some impurity to the pure semiconductor so that its conductivity can be increased, and there is two types semiconductor, P-type and N-type semiconductor. Means extrinsic property, that is P-type and N-type. P-type means in P-type semiconductor there is majority of charge carrier is hole, and for N-type semiconductor here majority charge carrier is electron. How P-type form? When we add trivalent. Clear? If we add trivalent material to the P-type semiconductor and pure substance, or you can say pure form of metal, if we add pentavalent, then we get N-type semiconductor. Clear? So now let's start. Electrical conductivity of a semiconductor. Suppose there is a semiconductor here and its length suppose L, total length of the semiconductor L. Clear? If we apply potential difference across the semiconductor, and here positive potential and this is plus and here minus sign, so you know that electric potential or electric field always start from higher potential to lower potential, or you can say this is positive terminal and here we get positive side and this terminal is negative, and this is the direction of direction of electric field, and its direction always towards positive to negative direction. And what is the direction of force? The relation between force and electric field, that is QE. Clear? But inside the semiconductor it possesses both hole and electron. Simply you can say the hole are positive charge and electrons are negative charge. And F equal to Q means Q we have to take here. So if this is positive charge, then direction of force or direction of electric field, direction of force are equal. But when this is negative charge, then the direction of force which opposite to electric field, so that this is the direction of electric field. At that time the electron experience a force opposite to electric field, so attracted towards the positive direction. Clear? And that's why if electron attracted towards the positive direction, then it increase the conventional current, you can say that is I due to E. Clear? Due to electron that develop a current, or here positive charge, it will experience a repulsive force and attract towards this direction, or you can say this is positive direction or positive charge or hole, and the direction of electric field. Now the direction of force is along the direction of electric field, so that this hole attracted towards negative direction and it increase the conventional current, that is IH. Clear? So total current here, total current flowing through the circuit I, and the total current can be right here due to the sum of conventional current due to electron, and I equal to IE plus IH. Electron and hole, which is we get total current I is here. Clear? But we already know the relation between current and drift velocity, that is I equal to NEAVD. What is VD? VD means drift velocity. Suppose I am taking here the drift velocity of electron VE and drift velocity of hole, that is VH. And what is N? N means number of electrons per unit volume. Number of electrons per unit volume. So here we can take, let that is Ne and NH be the electron density or density of hole, electron density and density of hole respectively. Clear? And what is VE? And second point, here VE means VE and VH, drift velocity. Drift velocity of an electron and hole inside the semiconductor. Clear? Because in semiconductor crystal, the charge carrier is electron and hole. Clear? That means it only allow to the current, we already discussed, only one direction, this direction. So here VE means drift velocity of electron and this is drift velocity of hole in this case. Now look at this case number 1. If we substitute all the value here, then we will get, that is I equal to IE means, I can write here IE means here NE and this is VE. So if you write here, that is NE means density of electron into electron area, and this area of cross section, simple you can say A, and charge of electron E, and here A, drift velocity VE, similarly NH EAVT. Clear? And if we take common here, then this term will be common. So EA equal to NEVE plus NHVH, drift velocity for hole. This is equation, second equation. But we already know, if there is electric potential, electric field E and total distance L, then we have a relation, that is E equal to potential by L. Here potential V. Clear? This is higher potential, you can say V, and here potential 0. So potential difference across two ends of the semiconductor, that is V minus 0 equal to V divided by L, or you can write that it's V equal to E into L. So potential difference in terms of electric field and length. So you can write here, that is EA into NE, and here V, or this is V. And mobility of charge carrier, you already know, mobility represented by mu equal to drift velocity by electric field. Clear? This is mobility of an electron, you can say. So mobility of electron can be write mu E equal to VE by E, and mobility of hole you can write, that is VH means drift velocity of hole divided by E. If we use this relation here, that means VE equal to mu E into this, and VH equal to here mu H into electric field. Now use this value here, then we will get EA NE VE, and VE is here mu E into E plus NH, VH is here mu H and electric field E, and common term is E electric field here, so you can take it out. So EA NE mu E plus NH, that is mu H. This is general expression. But here electric field E equal to V by L. What is V? V is not drift velocity. V is here potential difference across two ends of the semiconductor and divided by its length. So you can replace here E equal to V by L, that is V by L. So VEA by L, NE mu E plus NH mu H, and again I here. So we already know, according to Ohm's law, V equal to IR, and resistance of the conductor can be write potential difference divided by current. Clear? This is general relation. So here we can take V is here. So I by V equal to, the remaining term is here, I by V equal to EA by L into Ne mu E plus NH mu H, or here I by V which is equal to 1 by R, so you can replace here, that is 1 by R equal to EA by L Ne, clear, Ne mu E plus NH mu H. This is general expression. But if you want to find the resistance of this semiconductor here, actually we have to compare here the resistance increase or resistance decrease. So in this case, if you are to write the resistance, then R equal to L divided by L divided by EA. EA and mu E 1 by Ne mu E plus NH mu H, clear, and R can be write L by A into 1 by E mu E Ne, or Ne mu E plus NH mu H, and this is general expression. Or we already know what is resistance. Resistance is directly proportional to length and inversely proportional to area of cross section, and there is one constant resistivity rho L by A. This is general expression, clear, or you can write here L by A into rho. If you compare this equation 1 and 2, now compare the equation, comparing equation 1 and 2, you will get R equal to R, L by A, but rho is density, sorry, resistivity of the material. So resistivity can be write resistivity of semiconductor rho, which equal to 1 by E times Ne mu E plus NH mu H. This is the formula of resistivity. And if we change the total substance, then resistivity also change, clear, okay. Now if this is resistivity, and you already know what is conductivity, you can also find this material conductivity here sigma, and sigma equal to 1 by rho, means 1 by resistivity we get conductivity, but resistivity is directly proportional to conductivity. If resistivity increase, then resistance of the conductor increase, and electrical conductivity decrease. Resistance increase means oppositional factor increase, so current increase, in this case decrease, that means electrical conductivity decrease, clear. So 1 by R you can write here, that is E mu E Ne plus NH mu H, clear. So this is the expression for conductivity. Now if we discuss case number 1, for intrinsic semiconductor, so in this case, number of electron equal to number of hole. Suppose I am taking here Ni, number of electron equal to number of hole, and number of I is here, means here the concentration of electron and hole are equal. In this case, which case? Means intrinsic semiconductor. So in this case we can write the resistivity of this semiconductor rho equal to 1 by E into, here Ne and NH are equal, so one term we can take common here, that is Ni into the remaining part, that is mu I plus mu H. Why? Because this is mobility of the electron and hole, and that mobility which depends on drift velocity, because drift velocity of electron and hole are different, clear. So this is the case. If we increase here the concentration, if we increase concentration of hole, or if we increase the concentration of electron, then this is a decrease, resistivity decrease, clear, okay. So resistivity decrease, if resistivity decrease, here Resistivity decrease means resistance decrease. If resistance decrease, oppositional factor decrease. If oppositional factor decrease, current conductivity, the flow of charge particle inside the conductor increase. That's why we get maximum current. Clear? So we can control the current. So semiconductor is important thing here. It can control the flow of charge particle. Now case number 2. Here I am writing case number 2. Case 2. And in case 2, first point, that is p-type semiconductor, means you can take extrinsic semiconductor, and first one, that is p-type. And in p-type semiconductor, the majority of charge carrier is whole here, so NH very greater or very much greater than the, you can say, number of electron. Actually, what is N? N is here electron density, and H is here hole density. Clear? So in p-type semiconductor, number of hole means majority charge carrier hole is maximum and minority is minimum. So electron is minimum. So in this case, you can write this term here, this term. So resistivity of the semiconductor can be write 1 by E into here. This term we can cancel. If we compare this total term, then this term will be negligible. Clear? So the remaining part we can write here NH, that is mu H. This is the resistivity. Which case? Resistivity of p-type semiconductor. Similarly, n-type semiconductor. In n-type semiconductor, number of density, you can say electron is large as compared to number of hole. So this is the relation. So in this case, we can neglect this term. So this term if you neglect, then the remaining part you can write resistivity of the semiconductor 1 by E into here Ne mu E. Clear? So conductivity of a semiconductor can be increased by increasing concentration of electron. By increasing concentration of electron means number of electron per unit volume. If we increase this term, then here resistivity decrease. If resistivity decrease, then resistance decrease. If resistance decrease, oppositional factor inside the current which is decrease. If oppositional factor decrease, then electron can free to move inside the semiconductor. That's why we get a maximum current. Clear? And so that we can increase the conductivity of a semiconductor, or we can increase the conductivity how? If we increase the number of concentration, or second thing, if we increase the temperature of the conductor. If we increase temperature, then electron get energetic and move towards positive direction, and we get the maximum current. Clear? So these are the expression of electrical conductivity of semiconductor. Now let's start. What is PN junction? PN junction is important factor in all the electronic device, and it is known as PN junction diode. Clear? So in this case, we have to join a p-type semiconductor with n-type semiconductor. Means one donor with one acceptor. Clear? Suppose I am taking here one p-type semiconductor is here and one type semiconductor is here. Clear? And same crystal, you have to take here same crystal. Or you can say, if you take one crystal, suppose I am taking here silicon crystal, and one end of the silicon crystal you can dope with p-type semiconductor, and here p-type, and other end you can dope, that is n-type semiconductor is here. Clear? This is a donor and this is acceptor. Clear? It donate electron and it accept electron. So in this case, the majority of charge carrier in p-type semiconductor is whole. So here majority of charge carrier is whole, like this. Clear? And minority charge carrier in p-type semiconductor is electron, we already know. But in n-type semiconductor, here majority charge carrier electron and minority charge carrier is whole. This is minority charge carrier. Clear? Okay. Now what is PN junction? When we add this p-type, or you can say one p-type and one type semiconductor for same crystal, means here silicon crystal, there is a junction, and this junction is known as PN junction, means separated. This surface is separated by P type and N type semiconductor. Clear? Or in this case you can take another one is here, layer. This is free, or this is electron. Majority of charge carrier electron is here, but hole is here. This is hole, majority charge carrier in P type semiconductor. So these are hole, and here minority charge carrier is electron. Now when we combine here P type and N type semiconductor, according to Coulomb force, if there is two opposite charges placed very close to each other, then they are attracted with each other with a force, and that force is known as electrostatic force or Coulombian force, you can say. So in this case, the electron which move towards the positive, because hole is charge, that is positive charge, so electron move towards the positive due to diffuse. Now electron combine with hole and diffuse or neutralize at this point. Clear? Similarly, this electron also jump here and this electron also jump here. Clear? Now if all the electrons jump here, initially this crystal, means silicon crystal, initially it is neutral state. When we already know, if there is a substance, if we donate one electron, then this substance will be positive. If this substance accept one electron, then this substance will be negative. So that's why this silicon substance or N type semiconductor is here, it donate a electron, it donate this electron towards P type semiconductor and diffuse here. That's why here develop a positive charge in this case. Clear? Similarly, when it receive one electron, then it will get negative charge. So there develop a negative charge is here, like this. Clear? Now one electron and one hole, electron hole, electron hole, electron hole in this region, this is known as, in this region now neutralize with each other. So there is a deficiency of electron and hole. That means this layer is known as, all the electrons are depleted. All the electrons are depleted or neutralized in this region. So this region is known as, from this point to this point, is known as a depletion region or depletion layer. Depletion layer. Clear? And there develop a, here you can say this region and another one this region. There is no charge. Now here total region is vacant. Why? Because electron hole in this region are neutralized and deplete. So it form a PN junction. Clear? Okay. And you already know, if there develop one positive charge and another one side which is negative charge, electric current or electric field always start positive and terminate on negative charge, so that there develop a electric field this direction. This is the direction of induced electric field, you can say EI, means induced electric field. Induced electric field. So when there induced electric field, this electron now never come to N type to P type semiconductor. Why? Because Coulombian force F is inversely proportional to 1 by R square. Obey inverse square law. If distance increase, then force decrease. So the electron, this electron are separated large distance. If you compare hole and electron separate large distance, so electron cannot move this direction to neutralize. Or another way you can say, when they develop a positive charge and here develop a negative charge and electric field start this direction, but electrostatic force and electric field relation QE. If this is a negative charge, you can say electron, then electric field direction, which always opposite to force, means the direction of force always opposite to electric field. That's why if electron try to move this direction, then it will experience a repulsive force. Why? Because electric field this direction, so force will be opposite, so it will experience a repulsive force. That's why this electron cannot move from one point to another point. Or if we already know, if there is one conductor and here higher potential, suppose V, and here lower potential 0, and the potential difference across the conductor you can say that is V. And what is the important thing? What is the significance of potential? This potential provide energy to the flow of charge particle because V equal to W by Q. Clear? So it provide energy to the flow of charge particle from higher potential to lower potential, depends on the nature of charge particle. But in this case, if there is positive charge and here negative region, then there develop a potential here like this, and this is positive and here negative. Clear? Because there is potential and this potential is support to the flow of charge carrier, but there is also a potential, and this potential which oppose the flow of charge carrier. Why? Because there are also positive charge and here negative charge, so electron try to move this direction, but electron cannot move from N region to P region again. Why? There is another type of potential. Suppose this is V naught, and this V naught is here. V naught is called potential, and here V naught is opposed here, opposed. But in this case, potential it support to the flow of charge carrier, but here potential which oppose means this is barrier. So this potential is known as potential barrier. Clear? It always opposed to the flow of charge particle from N side to P side. And this potential barrier for silicon crystal, that is 0.7 volt. This potential barrier, and this potential barrier for germanium crystal you can say 0.3 volt. Clear? Now this electron cannot move from N region, means N type semiconductor to P type semiconductor due to this potential barrier. Again, this region is known as depletion region, and here if you draw a diagram like this, I am drawing here. Clear? So you can draw depletion region like this. Clear? This region is known as depletion region or barrier potential, you can say barrier potential. Clear? And it is represented like this graph. Here this is barrier potential. Clear? So this is all about PN junction. So form a PN junction. But what is the symbolical representation of PN junction? Here P type semiconductor and here N type semiconductor, and the representation of PN junction diode like this. Here one arrowhead which represent P type, and one plate here and which represent, this is N type region and this is P type region. Clear? P type and N type region. Now we will discuss here the important thing, that is forward bias and biasing condition. Biasing condition means when we apply electric field to the PN junction diode, then there is two possibility. Means first possibility you can say, first one, or biasing condition. Biasing condition. So first possibility is here, that is known as forward bias. Forward bias. Clear? So what is forward bias? You have to remember one thing here. Forward bias means we have to use p-type semiconductor with positive potential and n-type semiconductor with negative potential. This is known as forward bias case. So here in this case, if we use here this is Pn junction, here p-type and n-type, this layer is known as depletion layer. This layer is D. Clear? And here p-type and here n-type. P-type means majority of charge carrier is here, that is hole, and minority charge carrier electron. But here the minority charge carrier electron, but the majority charge carrier hole is here. Now we have to apply electric field to this semiconductor crystal. Okay. So for p-type semiconductor, we have to use, or we have to connect it with a positive terminal of the battery. So here this is positive terminal of the battery and here negative terminal of the battery. Clear? So this is known as forward bias. For forward bias, we have to connect p-type semiconductor with positive terminal of the battery and n-type semiconductor with negative terminal of the battery. So this is case. Clear? And here suppose potential difference between 2 points is here V. Now this is initial case. Okay. Or in this case, this is initial barrier. You can say potential barrier like this diagram. So this diagram I am again drawing here. Suppose this is potential barrier. This potential barrier. So here this is potential barrier. This is potential, or you can say barrier potential. Clear? Now this is initial case when there is no battery connected to the PN junction, right? This point is known as junction, and there is a potential barrier, negative potential, and this is high potential. Clear? For silicon crystal, if we take silicon crystal here, then the potential barrier is here 0.7 volt. Means if we supply this voltage, suppose 0.5 volt, then there is no current in the circuit. Why? Because there is a barrier in between p-type and n-type semiconductor. First, we have to eliminate this barrier applying heavy voltage or applying more than this barrier voltage. So if we increase this voltage, suppose 0.8 volt, then current flowing through the circuit. Why? Because here the applied potential which is greater than the potential barrier. Now potential barrier decrease. Clear? So now if we apply a potential difference across p-type and n-type semiconductor, and this potential should be greater as compared to potential barrier. Clear? Here 0.7, and I am drawing here a characteristic graph. This graph is known as VI characteristic. VI characteristic. This is for forward bias. Clear? And here I am taking potential, this potential, and here I am taking current, and this current always measure in milliampere. Clear? Or you can take in volt. Okay. Now when we apply this potential, this is positive terminal and here negative terminal, then this positive terminal attract electron. This positive terminal attract electron, or it push to this hole, because this is positive charge, positive potential is here, so it experience a repulsive force this direction. All the holes are experience a repulsive force this direction, and similarly negative potential is applied to the n-type semiconductor, so electron experience a repulsive force towards this direction. That's why, or you can say, if we increase the electron, because this is negative, if we increase the electron and if we increase the hole, then the number of majority charge carrier or the number of concentration, n type means electron and p type means hole, increase, so that they repel each other, so that this depletion layer decrease. So we have to increase this concentration in such a way that when this depletion layer decrease and finally vanish, when this depletion layer vanish, at that time the electrons flow from negative to positive or n type to p type semiconductor, and the hole always flow from now positive to negative terminal, or positive p type to n type semiconductor. Clear? First we have to deplete, first we have to eliminate this barrier by applying potential. That's why it is known as forward bias, and in this case a current flowing through the circuit, that is I equal to, you can say, that is IE plus IH. Clear? And in this case the potential barrier which is decrease. So this is initial case, or you can say this is a depletion layer D. For forward bias case, this depletion layer decrease, so that you can again draw this diagram like this. Clear? And here this depletion layer like this. Clear? Now this is depletion layer. Now depletion layer decrease. Initial depletion layer, if we apply potential here, a battery, then depletion layer decrease and finally vanish. And this distance is known as here, that is potential barrier. When we apply here, that is 0.7. But this volt must be greater than 0.7 volt to flow of the current here. Clear? But initial case, when depletion layer is not completely eliminated, at that time there is no current flowing through the circuit. When current will flow through the circuit? When? Because we increase this potential 0.1 volt, 0.2 volt, 0.3 volt, 0.4 volt, 0.5 volt, 0.6, 0.7 volt and 0.8 volt. At this time the current increase, but there is no current. Why? Because this is just limiting value. Then here this voltage is below or less the potential barrier. So in this case, if we mark here 0.1, 0.2, or suppose here that is 0.7 volt, then when we increase this potential up to 0.7, now current start increasing from here like this and increase rapidly. Clear? And that voltage at that time is known as knee voltage. Knee voltage means it is the limiting voltage. If we increase the voltage from knee voltage, then current increase sharply. This is sharply increased current. Clear? This is the case of forward bias. Clear? This is forward bias graph. This graph is important. Here depletion layer now is increased. So next come to reverse bias case. So what is reverse bias? Second thing, the biasing condition is known as reverse bias. So in this case we have to use a terminal of a battery p-type semiconductor with negative and n-type semiconductor with positive. Opposite polarity we have to use here. So this is the depletion layer D. Here p-type and n-type semiconductor is here, n-type. So majority charge carrier here, that is electron, and minority charge carrier hole. Clear? But here majority charge carrier hole, but minority charge carrier electron, and there is a negative side, and here there is a potential barrier and V naught for silicon crystal, and this is 0.7 voltage here. Now we have to apply a battery to the semiconductor crystal, and p-type semiconductor with negative sign, so negative terminal of the battery, and n-type semiconductor with positive terminal of the battery. Clear? Okay, now when we apply this potential, but initial case here, look at this diagram. This is the direction of electric field. This is the induced electric field, this direction IE. This is the direction of induced electric field IE. But this is positive potential, and here positive potential, and here negative potential. So electric field always start from positive negative. That means here electric field positive negative. This is applied electric field. Applied electric field and induced electric field, which are opposite to each other and they cancel each other. Clear? But in this case, this is the direction of electric field EI, and again here positive potential, and here positive sign and negative sign, and electric field always start positive to, this is applied positive to negative. That means this external electric field which support to the internal electric field, this direction, and again you can say electric field increase in this direction, so that electron cannot flow from one region to another region. Or another one thing you can clear here. Now this is positive charge, and this positive charge attract to the electron. If positive charge attract to the electron, suppose this layer vanish here, attract to the electron, and if this layer vanish here, now this depletion region increase, and now this depletion region come to this point. Similarly, negative charge, if negative charge now coming toward this direction and diffuse to one hole is here, suppose this hole attracted towards the negative charge, then this depletion layer now increase. This is depletion layer increase. Again it attract to electron, this electron now decrease. So that depletion layer increase in this case. Okay, if you draw here, I am drawing the depletion region is here. This is initial case, and in this case the depletion region increase. So you can draw, this is initial depletion region when there is no battery connected to the PN junction, but now the depletion region increase means this diagram will be like this diagram, or I am drawing here diagram, or this is maximum you can say here. Clear? This is depletion region for reverse bias. Clear? Now depletion region increase, and here if you draw this diagram is here, then you will get a diagram like this. Means depletion layer increase, and this is potential barrier also increase. This barrier also increase. But question arise here, if for p-type semiconductor majority charge carrier is hole is here, but there is also electron, means minority charge carrier, and also for n-type semiconductor there is also hole for minority charge carrier, and due to this positive charge it will experience a repulsive force toward this direction, and due to this negative charge it will experience a repulsive force towards this direction. In this case, if you draw a VI characteristic, characteristic for reverse bias. Reverse bias case. So this characteristic graph also important. I am drawing this characteristic graph here. This is known as reverse bias. So in case of reverse bias, there is a very small amount of current developed due to this minority charge carrier, and that current is known as leakage current due to minority charge carrier. Clear? If we increase potential, means here negative potential means opposite direction, because positive side contact to negative side. So if we increase this potential here, then very small current like this, very small current we will get here up to a certain value, and again we increase this potential. Now this potential barrier or depletion layer increase, and finally come to this state. And again if we increase this potential, then depletion layer is break, means vanish here. Clear? Depletion layer vanish means total PN junction now break, it will damage. So at that time the resistance of this semiconductor large, means you can say infinite, resistance increase, so that, and here resistance increase, and finally this is break. So we get a large current like this. Clear? And here up to a particular voltage, if we increase this voltage, suppose this voltage 1 volt, suppose, then at 1 volt total PN junction is break, then this voltage is known as, suppose 1 volt is here, this voltage is known as breakdown voltage, or you can say Zener voltage. We will discuss later what is Zener diode and Zener voltage. Clear? So this small amount of current due to this minority charge carrier, and that current is known as leakage current, and this graph is known as reverse bias graph. And here this direction is current, this current is known as forward current, and this current is known as reverse current, this direction. But reverse current always measure in microampere. Why? Because this is very small current, and this forward current which always measure in milliampere, which is positive direction, and this is a negative direction. Clear? So these are all about biasing condition of forward bias and biasing condition of reverse bias case. Clear? So in this case, for forward bias case, you can say I am writing here for forward bias case and reverse bias case. So this is the diode is here, or simply this is plate, and here P type and this is N type, or simply you can draw like this, here P type and here N type. What is forward bias? Forward bias means when we connect P type semiconductor with the positive terminal of battery, that biasing condition is known as forward bias. So we have to apply here higher potential positive and here lower potential positive, and this is known as forward bias condition. So what is reverse bias? If we apply here a negative sign, if we apply here a positive sign, this is known as reverse bias condition. Clear? Suppose I am taking on an example. Question may ask like this. Suppose there is a P types diode. This is known as diode. Clear? Name as diode or junction diode. PN junction diode, you can say. PN junction. This is symbol of PN junction diode. Here PN type and N type semiconductor is here. So suppose I am writing here, that is minus 3 volt and here minus 5 volt. minus 3 volt across p type and minus 5 volt across n type. Then my question is that this is forward bias connection or reverse bias connection. First question forward bias or second question reverse bias or third question none of these. Find answer here. One more question, you can find your council examination. So condition is that p type semiconductor always connected with higher potential and n type semiconductor always connected with lower potential. Same thing by here. So here minus 3 is greater as compared to minus 5. So this is forward bias connection. Clear? And if we take another one example here, like this, minus 3 volt and plus 5 volt. Here n type, this is p type. Then this is the reverse bias. Why? Because here lower potential and here higher potential. This is known as reverse bias case. Clear? This is forward bias and this is reverse bias case. Clear? So these are all about the PN junction and forward bias and reverse bias connection. Now come to the circuit diagram you can draw for forward bias. Forward bias circuit diagram. Now there is a forward bias, means here p type and n type is here, and here we have to use a rheostat like this, and there we have to use a battery, and this is n. Forward bias means n type semiconductor with connected with negative terminal, p type with here a positive terminal of the battery. So this is negative terminal, this is known as forward bias case, and this symbol is known as rheostat. Rheostat means we can change resistance, that's why we can change current flowing through the circuit. Now this is the direction of flow of current. Clear? So the important nature of this PN junction is that when current flowing through this direction means higher potential to lower potential, then it allow current pass through it. For reverse bias case, here p type and n type, this circuit diagram I am drawing here. So there is one rheostat and n type semiconductor connected with positive terminal and p type semiconductor is connected with negative terminal. Clear? And a very small current, now current flowing through this direction and it does not allow this direction, means here the junction diode will be break. Clear? So it only allow current when current flowing from p type to n type, it allow, but when it n type to p type, it oppose. That's why it is called unidirectional effect of semiconductor. First class we told you that this case for conductor you can apply current this direction and this direction. Insulator there is no current. For semiconductor you can apply current only one direction. This is the reason. Clear? So these are clear picture about PN junction. So what is PN junction? What is depletion layer? What is potential barrier? How potential barrier decrease? How potential barrier increase? And what is forward bias? What is biasing condition? Means forward bias and reverse bias condition. And most important thing is here the VI characteristic graph of forward bias and reverse bias condition. Clear? Thank you all.